Okay, fundamental theorem for line integrals. So we learned about line integrals in section 13.2, and now there is apparently a fundamental theorem for line integrals. Let's talk about it. Let me show you what it is first of all. This is the fundamental theorem of line integrals. So you let C be a smooth space curve given by a vector function, R of t, that traces out the space curve. Let a function f be a differentiable function of 2 or 3 variables whose gradient vector is continuous over the space curve. Well, I want to say this the right way. So you have the line integral there on the left, but it's the line integral of the vector field that's the gradient function. So if you are computing a line integral with respect to a vector field that's a gradient function, or equivalently, if you're trying to compute the work that a vector field given by a gradient function does in moving a particle along some space curve C, that work can be found by evaluating the function at the point where the space curve begins and the point, that work can be found by taking the difference by taking the difference of the function values where the space curve ends minus where the space curve begins. That's what that means. So, if you think about it, let me just sort of show you in practical terms what this really means. So here is what you just learned in section 13.2. The work is found by computing the integral of this dot product. So this is always true. Always true. Okay, for any vector field. Okay, always true. But of course, in the example we saw, it took some work to compute this. Okay, it did take some work to compute that integral. You had to find the parameterization of your space curve, and you had to compute the integral. Now, what the FTLI says, that again is the fundamental theorem of line integrals. What that says is, if you're going to compute the work, but your vector field F is equal to a gradient field, that's what this means, right? This here is a gradient field. It's a vector field, but it's a gradient field. Okay, if you're going to compute, hold on here. If you're going to compute that line integral, you don't need to do this up here. Okay, all you need to do is evaluate the function at the endpoint of the space curve, evaluate the function at the beginning point of the space curve, and take the difference. So, you know, a space curve C, okay, that is traced out by, probably should have this like this, that's traced out by a position vector, R of t, okay, from the origin, okay. This point here would be R of A. That's the beginning point of the space curve, and the end point of the space curve is R of B. So when you have, when your vector field is a gradient field, it's very easy to compute the work that the gradient field does in moving a particle along the path. Very easy. So this is a theorem, the fundamental theorem of line integrals is a theorem that we would like to try to use when we can, okay, because the first approach here is harder than the second approach. Now, sometimes you have to use the first approach. Like the example that we did, where we had a well, yeah, I'll just say sometimes you have to use the first approach, but sometimes you can use the second approach. The question is, when can you use the second approach? You can use the second approach if your vector field f equals the gradient of some function f. Okay, if that's the case, and the function f is called a potential function. Remember, we talked about that last time. So like, for instance, the gravitational field. Okay, that is, well, that is a conservative vector field because the gravitational field has a potential function. But let's go ahead here and continue on in the book. I mean, you have the key idea. Now, the proof of this theorem is not hard. The proof of this theorem is not hard, but again, what does this fundamental theorem mean? Fundamental theorem of line integrals. It says that you can compute the work simply by evaluating the function at the two endpoints and taking the difference. That's if you can find a function f whose gradient will equal the vector field f. Okay. Now the proof of the fundamental theorem of line integrals is not difficult. It's not difficult. So you are taking the dot product of the gradient field with the derivative vector of r, but the and that's equal to the partial derivative of f with respect to x times dx dt plus partial derivative of f with respect to y times dy dt. Well, it equals the integral of the sum of those products of partial derivatives. You see, the gradient of f in the components are the partial derivatives of f with respect to x, y, and no, I'm sorry. the gradient of f, the components of that vector field are the partial derivatives, right, of f. The r prime of t, that vector, its components are the derivatives of x, y, and z with respect to t. So by the chain rule, that summation there is simply equal to the derivative of your function with respect to r of t. Okay, for you to see that, I can show that. I can show why that's true. If you have, for instance, let me see here. If you have a function f of r of t, okay, you can write the function. The function is let's just do it with 2 dimensions, 2 variables. The function is itself a function of x and y, but then x and y are themselves functions of time. Okay, so if you, I want to do this right. If you were to find the derivative with respect to t of this function of rt by the chain rule, this would be what you'd have, right? And so the derivative of the function is equal to the chain rule expansion. Hopefully that makes sense. And so now, if you go back to the book here, they are doing it where you have a function of 3 variables. I showed you quickly for a function of 2 variables. But now you have the integral of a derivative. And the integral of a derivative, the integral with respect to t of a derivative with respect to t, just gives you the functions, gives you the difference of the function values at the starting and at the beginning and endpoints of the position vector. That's the fundamental theorem of line integrals. And we use the fundamental theorem of calculus to get to from the 3rd step to the last step, right? So this is really a wonderful, wonderful thing. And it means also what's called independence of path. It means independence of path. So let me show you what that means here. Let me go down here. We'll look at an example, but so let's say you have 2 curves, paths, that have the same initial point and terminal point. So in general, the line integrals for those vector functions along the 2 different paths are not equal. Okay. However, if your vector field is the gradient function, then those line integrals would be equal, because the 2 paths, even though they could look like different paths, they start from the same beginning point and end at the same ending point. And the fundamental theorem of line integrals, just the line integral itself is computed just by taking the difference, right, of those endpoints of the when they're evaluated in the function. So what we say then is, and I want to just let me just take this off here. So in other words, the line integral of a conservative vector field depends only on the initial point and terminal point of the curve, because a conservative vector field is a vector field f such that it equals the gradient of some function, and you can find the function. Okay, so that's like gold, right? If you can do that, that's like gold, right? All right, so let me just see here. The question is now, well, another thing too that I'll mention here. Hold on, let's see if I can. Hold on. I'm trying to highlight this, but it's not liking it. There we go. So if you had a, come on. All right, it just is going to stick with that. So if you had a closed path, in a conservative vector field, if the work that the force field does in moving the particle once around the path would have to equal 0. Right. So but let's just talk about the key thing at hand here for now. Okay, we have a line integral that we want to compute. Well, a line integral of a vector field that we want to compute. If we can find a function f okay, that such that the gradient of f equals the vector field, then the line integral of this vector field would equal this line integral, and that would just be then equal to that difference. And I'm sorry, it's a little bit, let's try to make it fit here a little bit. Hold on, I'm going to get it to work. Hold on. Give me 1 minute here. Right. So this function f here, this function f is known as a potential function. So from now on, when we are looking to compute this work integral, we should ask ourselves, hey, is there a potential function for that vector field f? Because if there is, then by the fundamental theorem of line integrals, it's easy to compute the work. So now the question is, how do we find the potential function? How do we find it? Well, let's go back to the book and see if we can get some ideas. Okay. So the question remains, how is it possible to determine whether or not a vector field F is conservative, meaning it has a potential function? Well, here's one way. Suppose it's known that the vector field F is conservative, where P and Q have continuous first-order partial derivatives. If that's the case, then the components P and Q would have to equal those partial derivatives with respect to some function, because the vector field F would equal the gradient of some function. Well, what you can do is you can differentiate the P and the Q, the P with respect to Y, and differentiate the Q with respect to X. And if you do that, you're going to get then that the partial derivative of P with respect to Y equals the partial derivative of Q with respect to X by Clairaut's theorem. Because Clairaut's theorem says, if you remember that, back, I believe that was section 11 point, let's see, 11.3. The mixed partial derivatives of F are equal to each other, and it doesn't matter the order in which you do the differentiation. Yeah, that's Clairaut's theorem, section 11.3. So this gives us a way to find a conservative vector field. This theorem, okay, says that if you had a conservative vector field, then with components P and Q, then the partial derivative of P with respect to Y would equal the partial derivative of Q with respect to X. And in fact, being a little more general, because here we assumed we had a conservative vector field, but we can be a little more general, like they have here in Theorem 6. If you have a vector field, then if the partial on an open, simply connected region D, and we're not going to get into, let's just keep it simple. Let's just, for now, we have a vector field. You know, it is basically partial derivatives are continuous throughout the vector field. If the partial derivative of P with respect to Y equals the partial derivative of Q with respect to X throughout the region D, then you have a conservative vector field. Okay, and they have some pictures here. Let me just see here. They have some pictures. Let's see. They have examples in the book, but look at figure 8 and figure 9 here. So look at figure 8, and you see that if you look at that closed space curve, if you pick a point on the space curve and you go from that point back to that point, okay, in other words, what I'm trying to say is this: if you I want to say this the right way. So if you have a space curve and it's closed, okay, and you know this is your space curve C, and let's say you start at this point here, okay, so that's R of A, and that's the beginning time is A, and you go once around the space curve, then you're at a later time, so like R of B. So in this case, you know, R of A, I'll note it here, R of B equals R of A. So for a closed space curve, your starting point equals your ending point, right? Because it's a closed space curve. Well, in a conservative vector field, it wouldn't matter in a conservative vector field by the fundamental theorem of line integrals for a conservative vector field. Okay, FTLI. Okay, if the gradient of f is equal to the vector field, in other words, you found a potential function. You found a potential function such that the gradient, such that the vector field f equals the gradient of the function, then the work is simply equal to the function evaluated at the endpoint minus the function evaluated at the beginning point. But that's going to equal 0. That's going to equal 0 when you have a closed curve. When you have a closed curve. So for a closed curve, the work that the force field does in moving the particle once around the path should equal 0. Should equal 0. Okay, so in this conservative vector, so you have a conservative vector field then. You have a conservative vector field. Okay, and probably when I write this down here, probably instead of gradient f equaling the vector field, I should probably write the vector field f equals the gradient of some potential function f, because you have to find the potential function, right? You have to find it. So let me just see here. I'm just looking. Yeah. So if we go back to those pictures, figures 8 and 9. Figure 8, if you look at that closed path, does it look like based on the vector field, like if you're in the first quadrant, does the vector field seem to, I want to say this the right way, does the vector field seem to help the particle move along its path in the first octant for figure 8? Do the vectors sort of push the particle along the path in figure 8 in the first quadrant? It's a yes or no answer. Look at the vectors, look at the space curve. Pretend those vectors are like wind, and wind, is the wind helping move the particle move along that path in the first quadrant? Marina says yes. What about the second quadrant? Are the vectors helping the particle move along the path in the second quadrant? They are, Lexi, that's right. What about the third quadrant? Do the vectors help move the particle along the path, its path in the third quadrant? Overall, yes, and the fourth quadrant as well. So overall, the work that this vector field does in moving the particle once around the path would be positive work. because the vector field is helping the particle. The net effect of the vector field is to help the particle move once around its path. So that would be an example of a vector field that is not conservative, because for a conservative vector field, the work would have to equal 0. However, if you look in figure 9, if you look at that vector field and you look at those paths there, those closed paths in figure 9, the vector field, well, if you look at the path C1, the first quadrant, the vector field is hurting the movement. But in the second quadrant for that path C1, the vector field seems to also be hindering the movement. But then in the third quadrant, the vector field is helping the particle move in the third quadrant along its path. And in the fourth quadrant, let me just see here. I gotta, let's see, the fourth quadrant, the vector field is, I want to be careful. So basically what I'm trying to say in figure 9, it's not perfectly obvious, but basically if you look at the vectors overlaid on that closed path in figure 9, the C1 path, sometimes the vector field's helping the particle move along the path, sometimes it's hindering the particle moving along the path. But where the helping occurs, the work is positive. Where the hindering occurs, the work is negative. The net total is going to be 0. So figure 9, the vector field there for the path C1 is actually it's a conservative vector field. Okay, so I'm just trying to give you, and I'm trying to help you intuitively understand what these vector fields, what it means for a conservative vector field, what it would look like, basically. Gravity is a conservative vector field. Okay, gravity is a conservative vector field, because look at what I'm going to do here. I'm going to start at a point. Let's say it's an airplane. It's an airplane. Okay, here's an airplane. Okay, like those folks that fly the airplanes and do like the what's it called, like the tricky maneuvers. I'm going to do a loop-de-loop. Here I am. I'm going up. I'm going up. I'm going up. I'm going to do a loop-de-loop, but this is, so far, I'm going up. Is gravity helping me or hurting me in going up? Is gravity acting against the path or with the path? Against it. That's right, Norina. So work is negative. Okay, work is negative. Work is less than 0. Gravity acts against that part of the path. Now what I'm going to do is I'm going to do this. Woo. Okay. For this part of the path, from here to here, so we did part 1 of the path. For part 2 of the path, would the work be positive or negative? Part 1, part 2. This is part 2 here. Is the work positive or negative there? Is gravity acting? It's right. Good, Lexi. Gravity's helping me move along that part of the path. So work is positive. That's right, Lexi. So gravity helps. Well, the sum total of work would equal 0 because gravity is a conservative vector field. If you move along any closed path in a gravitational field, the work's going to equal 0. Doesn't matter what the path is, by the way. The path could be a crazy path, you know, like woo. It could be any path, right? The work's going to be positive. There's, you know. So I hope this is helping. Let's do an example now where we actually need to compute some work. All right. So let me give you a moment to copy this example down. Okay, now for this problem, I'll mention, let me just get my three-point font. So if we were to find the work this way, using the general definition of work, okay, if we were to find the work this way here, it would be very hard, I think, because evaluating this part here, f of rt, where the way rt is defined, that would be maybe even impossible. So let's see if the force field, this force field here, I mean, it may be possible, but let's see if the force field is conservative. Okay, let's see if we can work this problem out that way. So, of course, we want to see if we have a conservative vector field. And it turns out we do, because the partial derivative of p with respect to y equals the partial derivative of q with respect to x. Let me let you copy this down. Please let me know if you have any questions. All right, well, now that we know we have a conservative vector field, let's find our potential function. So how do we go about this? Well, of course, for this statement to be true, where the gradient of the function equals the vector field, this means that the partial derivative of f with respect to x would have to equal 3 plus 2xy, right? That's the p there. And the partial derivative of f with respect to y would have to equal the q component of the vector field. So I have two pieces of information, and based on those two pieces of information, I can find the function f. So let's say we worked. Let's say that we worked with the first equation. And I want to know what my function is, right? I want to know what's my function. Well, I know what the partial derivative of the function with respect to x is. That equals 3 plus 2xy. How can I go from partial derivative of f with respect to x? How can I go from there to get back to the function itself? What would I have to do? What would I have to do here with this partial derivative? If I have a partial derivative of f with respect to x, and I want to find out what the function f is, how do I get from the partial derivative to the function f? Integrate. That's right, Norina. The function f would be an antiderivative. Would be the antiderivative of the partial derivative of f with respect to x. So that's what we have to do. That's what we have to do. So on this page, I just rewrote the two equations, and I'm going to integrate the first equation with respect to x. When I do that, I'm going to get f of xy equals, so you know, what's the antiderivative with respect to x of 3 plus 2 times x times y? It would equal 3x plus x squared y plus a function of y. We have to allow for a function of y to be added on, because the derivative of a function of y with respect to x is equal to 0. So this is the most general antiderivative possible. I'm not going to say plus a constant. I'm going to say plus the function of y. Now, maybe that function of y will equal a constant, but I have to allow for that. That it could be, you know, some function of y. Now that we know something about our function, well, we do know something. We do know that our function f of xy equals 3x plus x squared y plus g of y. But the function isn't useful unless I figure out, you know, what is this function g of y? What is it equal? Well, now let's make use of the second equation. The second equation says, hey, the partial derivative of the function with respect to y equals x squared minus 3y squared. Well, all right, why don't I differentiate this new equation I have, I call it equation 3, with respect to y. So the derivative of partial derivative of f with respect to y would have to equal then 0 plus x squared plus g prime of y. make that a little bit more clear. So now we have that the partial derivative of f with respect to y equals x squared plus g prime of y. Okay, well, I can compare equations 2 and 4. I can compare them. And if I can compare them, I see that g prime of y would have to equal negative 3y squared. That has to be the case. And therefore, g of y would equal negative y cubed plus k. Now that k is a constant. It is some constant. We don't have to specify it. But now we know what g of y is, and so I can substitute in this g of y here into my potential function, and I have my desired potential function. Truly fascinating, really. Okay, take a moment to copy it. Let me know if you have any questions. Okay, so now that we have our potential function, and you know, you're probably thinking, well, gee, Dr. Duty, you know, this just kind of worked out nicely. They're always going to work out nicely when you have a conservative vector field. You will always be able to find that a potential function. And now what we want to do, remember what we're trying to do here. We're trying to, you know, we want to compute the work that this vector field does in moving the particle along that path, along that curve C. Okay, so we have the potential function. Let's use the fundamental theorem of line integrals. So if we do that, okay, this is the fundamental theorem of line integrals. And I have to evaluate the position vector at the end time and the starting time. So that's what I do here. The starting time was t equals 0, and the end time was t equals pi. And so this allows me to compute the position vector, the beginning position vector that has coordinates 0, 1, and the ending position vector that has coordinates 0, comma, negative e to the pi power. Let me give you a moment to copy this down. Please let me know if you have any questions. Okay, so now we're going to use that fundamental theorem of line integrals. And we need to compute the function at the point 0 with coordinate at the point with coordinate 0 and negative e to the pi power, and at the point with coordinate 0, 1. All right, let me know when you're ready, and I'll move to the next page. All right, Norina's good. All right, Norina's good, and we'll. All right, Logan's good. Yeva's good, wonderful. Okay, Simon. All right. So now we're going to evaluate this. All right, so let me go ahead to the next page here, and I can always come back, but I think give another minute here. All right, so let's finish up the problem. Now keep in mind, our function f is equal to 3x plus x squared y minus y cubed plus k. Okay, so even though we don't have a value for the k, it's okay. That's all right, because the k values, when we evaluate the function at the endpoints and subtract, the k's cancel out. Simon, I can go back to the previous page then after, if you're Want to make sure you're comfortable. I'll go back if you need to. You know, let me get through this page and okay, all right, good. So we end up getting, in the end, we end up getting that the work is equal to e to the 3 pi plus 1. And that means that if we were to graph the particle moving along its curve c and overlay the force field, if we were to look at a picture of this, and you could create a picture of this using the MATLAB program that I am giving you in Blackboard for section 13.2. It's a second program. You could actually see that overall the work is that this vector field is helping the particle move along its path. And that's fine. You remember, the path is not a closed path. If it were a closed path, the work here would have to be 0 if the path were closed. But this path, if you look at the R of t, which has components e to the t sine of t and e to the t cosine of t, where t goes from 0 to pi, that's not a closed path. So it's an absolutely fascinating concept, this fundamental theorem of line integrals. Truly fascinating. They have a section on conservation of energy in section 13.3, where they talk about how if you, let's see here. I'm just looking at it. I don't want to get too deep into the weeds, but how many have seen conservation of energy maybe in one of their classes? Okay, Yeva has, Narina has. Well, they talk about it in regards to this fundamental theorem of line integrals in towards the end of section 13.3. So it might be worth some good reading. Let me see here. There was let's see. All right. So are there? I will mention one more thing here. I want to show you something in the ebook as well. Hold on. Okay, so hopefully we're good here. Let me go to the ebook. They have an example 5. Now we did a problem where we had the vector field and the space curve were in 2 dimensions, 2-dimensional space, the xy plane. This process of finding a potential function for a conservative vector field in 3-dimensional space is similar. Let me just bring this up. I want to give you a little time to work on this, so I'm just going to touch on this. Let's see here. Yeah. Come on, I want to highlight this thing. Yeah, there we go. So here they say find the potential function for a 3-dimensional vector field. Now, you do not have yet criteria to determine if a three-dimensional vector field is conservative or not. You have not learned about criteria that will help you learn to do that. But there is criteria that can tell us that if we have a conservative vector field, and it relates to showing that the curl of a vector field equals the zero vector. But that doesn't come up until section 13.5. In section 13.3, when you have a three-dimensional vector field, they're just going to tell you that it's conservative. In other words, you're not going to have in 13.3, I want to say this the right way. So like for two-dimensional vector fields, you'll have problems in section 13.3 that say determine whether or not this vector field is conservative. And what you would do is you would see if the partial derivative of component P with respect to Y equals the partial derivative of component Q with respect to X. However, for a three-dimensional vector field, you have not learned yet about criteria to establish if that vector field is conservative or not. So basically, they're going to just give you conservative vector fields when you have three-dimensional vector fields. So in this case, they say, okay, here's this vector field function. Look at those components. Wow, pretty interesting. Find a function f such that the gradient of f equals the vector field f. Find a potential function. So they're going to go through similar steps to the example you just learned about. Hold on here. Let me just take this off. So what you would do in this case, you would have three partial derivatives, and you set each one equal to the respect to the component that of the vector field that you should be setting it equal to. Okay, and then what you have to do is you have to find that potential function. So what they do is they say, okay, here is this first equation, the partial derivative of f with respect to x equals y squared. So what are you going to do? You're going to integrate that with respect to x, just like the previous problem that you had for your notes. Now the antiderivative of y squared with respect to x is y squared times x. But there's more. You have to add a function to it. The function that you would add would be, so the antiderivative of y squared with respect to x is x squared times y, or x times y squared. Hold on, let me make sure I'm looking at it too much here. Yeah, the antiderivative of y squared with respect to x is x times y squared, plus a function g, that's a function of y and z. You see, now you have to allow for the y and z variables, because if you differentiate g with respect to variables y and z, you would get 0, you see. So the most general antiderivative is our function f equals x times y squared plus g of yz. Then what you're going to do is you're going to differentiate that function with respect to y. And when you differentiate that function with respect to y, you're going to get the partial derivative of the function with respect to y equals 2 times xy plus the partial derivative of g with respect to y. You compare that partial derivative with respect to the partial derivative given above in the problem, and you'll see that g, the partial derivative of g with respect to y, is equal to e to the 3z power. And so now, hold on here, I went too far. Now, okay, you can figure out what g of yz is by integrating that. Let me just highlight it here. If you, hold on, it's kind of temperamental here. There we go. Yeah, if you integrate that partial derivative of g with respect to y, which equals 3 times z, if you integrate that function with respect to z, you'll get g of yz equals y. No, I'm sorry, you're integrating that function with respect to y. If you integrate that with respect to y, you'll get g of yz equals y times e to the 3z plus h of z. Now you have your, now you specified your function this far. Okay. You've specified it this far, and then you're going to compare that function with the, hold on, compare that function with equation 13 above. So I mean, you can just look at the example 5, and but I'm just sort of giving you some details on how you would do the process with a vector field in a three-dimensional vector field. On that note, I want to give you 10 minutes here to work on, I'm going to give you a little more time to work on section 13.2, but I'll make 13.3 available if you want to work on that. Are there any questions before I stop the recording? Who's sort of feeling reasonably good? All right, Yeva's feeling reasonably good. I always like to end the recording with, hopefully people are, I mean, obviously you have to practice, but you get the general idea of these conservative vector fields? Okay, good. Alexander, Norina, Logan, excellent. And Christopher, and you know, again, like gravitational field is a conservative vector field. It's a beautiful thing. Conservative vector fields are beautiful things. We love them. We love them. Okay, and luckily they encourage nature a lot. All right, so let me go ahead and stop the recording. Excellent.